All right, everyone. So today we're going to be talking about special functions, and our essential question is going to be how are piecewise functions graphed? And our target will be to graph and interpret piecewise functions. So a piecewise function is a function made up of pieces of equations with restrictions. So the easiest way I can explain to you what a piecewise function is it's basically if you had 3 different graphs or 2 of different functions and you cut them out into sections and kind of pasted them together. So you have like one function here, one here, and one here. So one picks up where the other one leaves off. So that's what a piecewise function is. Each piece basically lives in only one neighborhood, and you can think of the restrictions as fences separating each house, okay? Now, with the restrictions, if we use a less than or equal to, greater than or equal to sign, that gets a closed circle, and that means that that's basically the owner of that particular point, okay? An open circle is what we use when we have a less than or greater than sign, and that means that they basically get really close to that border, but they don't actually take on that point, okay? Kind of like if you're talking about like a neighborhood and there's fences, like you can get really close to the other house, but you don't actually own that property that is right on the other side of you. So, let's talk about how we graph these. So there's several different ways to go about it. In my opinion, the easiest way to do it, take this off, 'cause I can. Okay. So the easiest way to do this is to actually look at the restriction first. So I always start at the restriction because it gives me a good indicator of where I should be. So the restriction on this one is x is less than 1. So that means that this particular function is going to take on all values that are less than 1. So the first thing I do is I plug in 1 in for x, right here. I plug this value into here. So 1 plus 2 is what? 3. So the 1 that I plugged in is my x-coordinate, and the 3 that I got as the output is my y-coordinate. And you're going to plot that. And are we going to use an open or a closed circle here?
Open.
Open. So 1, 3, we put an open circle. Now from here you have to think logically through the process. If we're talking about values of x that are less than 1 means we want to go smaller than 1. So what's a value smaller than 1? 0. So we're going to plug in 0. What's 0 plus 2?
2.
Good. So the coordinate is going to be whatever you plugged in, comma, whatever you got. So 0, 2. And this is going to be a closed circle. Anybody know why this is closed circle? Yeah, go ahead.
Where's the 0 from? Wait, you got 0 plus 2?
Okay.
Sorry.
No, it's okay. So your whole idea here is to try to graph this function when x is less than 1. So less than 1 means it takes on every value that is less than 1. So I'm just picking another value that is less than 1.
And then you add the other. Okay, I just didn't like, 0 wasn't actually in it, it was just on the graph.
No, so then once after you plug in the actual restriction, you're going to pick some other values that would be included on the restriction.
Okay.
So I picked 0, for example. I plug 0 in, that makes it my x, and the value I receive, my dependent variable is y. So I get the point 0, 2, and the reason that that point is included is because 0 is definitely less than 1, so it would be included on that graph, okay? Now, once you start seeing the pattern, if you wanted to, you could plug in -1, but you can see where this graph is going, right? Can everybody see that pattern? It's going down 1 over 1, just like this. And then I can just connect it. So I'm going to connect the graph, and I'm going to put an arrowhead here. Does anyone know why there's an arrow? Yes.
Because it like continues onward.
Very good. So x is less than 1 is infinite, right? It goes on forever in the negative infinity direction. So we dealt with the first part of our graph. Now we're going to deal with the second part of our graph. So that's the lower part here. I'm going to do that in red. This part right here. So x is greater than or equal to 1. The first value I'm going to plug in is 1. 1 minus 1 is 0. So my coordinate is 1, 0. Is that going to be solid or open?
Solid.
Solid because of the nature of the inequality sign with the line underneath it. So I got that point. Now I'm going to pick some values that are greater than 1. Because I want to get more values from my graph. So what's a value greater than 1? Good, 2. So I'm going to plug in 2. So that's going to be 2 minus 1, which is?
1.
Good. So my coordinate is going to be?
2, 1.
Very good. So I have a point at 2, 1. And then you can see it's just this aligned with a slope of 1, right? So it's just going to go up 1 over 1. Yes?
How come the first arrow has one open and the rest are closed?
Because it takes on all these other values that are less than 1. It just can't take on actual 1.
Okay.
Does that make sense?
Yeah.
Okay. So then from here, I will connect this and put an arrowhead in this direction because it's going to go on forever as x values greater than or equal to 1 is infinite, right? So does anyone have any questions about that?
No.
You starting to feel okay with these a little bit? Okay, getting the gist of it. And it's going to take some time to really get the whole, picture, but. All right, am I good to move on to the next one?
Yeah.
All right, so on this one, we're looking at a 3-piece piecewise function. There's 3 pieces. So we're going to work with the first piece first. I usually work top to bottom. It's easiest. So I'm looking at x is less than 1. The first value I'm going to plug in is automatically going to be what? 1. So you always plug in what the restriction is first. 2 times 1 plus 1 is? 3. So that coordinate is going to be 1, 3. And is it going to be open or closed? Open. Good. Now I want to pick a few more values, at least 1 or 2 more, so I can get a look at my graph. So what's another value I should plug in there that would be on my restriction? 0 would work, perfect. So we're going to take the same equation and plug in 0. That's going to come out to be what? 1. So that's going to be 0, 1. And remember, 0, 1 is included because 0 is truly less than 1. So it fits on the restriction. We don't need to deal with any open circles there. So you can do another point of -1, and if you do -1, it's going to come out to be -1. You can trust me. And then I will just connect it. Better than that, hopefully. It's really hard to do with this. Yes, what's up?
Why is the other 2 points closed circles?
So the whole idea of open circle is it can't actually be 1 because x is strictly less than 1. But 0 is actually less than 1, isn't it? So therefore it's included on that domain. Yep. So does it? Yes.
For the equations on the side that you solved, how do you know when to put 1 and 0?
So the reason I know what to plug in is I look at the restriction right here, and I always plug in what that restriction is first. Then I look at its values of x that are less than 1, so I pick a value less than 1. That would fall on my, yep. So you always want to pick within what's going to be within that restriction. Does that make sense? Okay. Any other questions before we try the next part? All right, let's go ahead and try the middle part. So the middle one is a little bit unique because this one is bound. This domain is bound. Does everybody know what I mean by that? So the domain is not going to go off to infinity. This is going to be like a little chunk of a line. On both ends, it's going to terminate. So the first value I'm going to plug in is going to be the first endpoint, which is 1. Okay? So that's going to be -1 plus 2, which comes out to be 1. So my first point is going to be 1, 1. And is it going to be solid or open? Solid, because of the nature of the inequality sign right here. That tells me it's going to be solid. Now, I want to pick another value that's between 1 and 3. What's that? 2. So now I'm going to take my equation and I'm going to replace x with 2. -2 plus 2 is? 0. So I'm left with 2, 0.
That's the open, right? Open circle?
Yes, I put it on the wrong spot though. No, it's a closed circle. Do you know why?
Oh, because it's in between the 3 is going to be open, correct?
Yes, the 3 is going to be open because that's the one that the value it actually can't take on.
Okay, yeah.
So the next value I'm going to plug in is the other endpoint, which is 3. So that's going to be -3 plus 2, which is -1. So 3, -1 is going to be our last point, and it is going to be open. So does everyone understand why that one is open? Very good. The 3 is not included due to the nature of the inequality sign right here. Okay? Yes?
And it doesn't have an arrow because the inequality is bound, right?
Exactly. The only time it's going to have an arrow is where one end is going off to infinity.
Okay.
And then the last one we're going to do is this one right here. Now, what do you notice about this equation right here, too?
It's just a 2.
It's just a 2. You can't plug anything in. Does anyone know what that looks like on a graph, y equals 2? Yeah.
Isn't it just a dot on the 2?
It's a dot on the 2, but it goes on another dot on the 2 for every x value, which eventually forms a horizontal line. So when you see these in piecewise functions, they're very, very common. These are what we call constant functions. Anybody know why we call them constant?
They don't change.
Good. They have a slope of 0, meaning they don't change. Okay, they just stay at 0 the whole time. So basically, when you go to plot the y coordinate, it's always going to be 2 no matter what x value it's at. So it's just 2 every time. So basically, we're going to start at our domain, which is at 3, so it's going to be 3, 2. And then it would be 4, 2. And if we had more space to graph, it would just keep going on forever. Like over here, just keep going. And be a perfectly horizontal line. So when you connect it, you're going to put an arrowhead going to the right because it takes on every x value that's greater than or equal to 3. So that's how you graph when it's just a number, okay? So does everyone understand our graph situation here? I'm going to erase some of this stuff so you can see a little better. Alright, so this is what a piecewise looks like. Now you also are going to need to interpret domain and range of a piecewise. So what's the domain of this function, or a function in general? Good, it's all the x values this function will ever take in its whole lifetime. And we know that most functions have an infinite lifetime in both directions. So let's think about what's going to happen. If this kept going, it's going to go wider and wider and wider and eventually take on every x value on the left, right? And over here,
What?
so see how this keeps going?
Yeah.
And it's going wider and wider and wider? So it's eventually going to keep going way out forever.
Oh, yeah. Okay.
Does that make sense?
Yeah, I thought you meant like it's gonna like pass through the X line. I was like, that
Oh.
doesn't sound right.
No, it doesn't need to pass it. It just means that it's going on forever to the left and going on forever to the right, which means that its domain is from -infinity to +infinity. Very good.
I get it now. I just like thought I heard you wrong.
You may also see somebody call it all real numbers. Just so you know. Once a student asked me why I was using a hashtag symbol, so
No way.
way.
That's embarrassing. I didn't even know it was a hashtag until I got to high school. I thought it was just a pound symbol, like everyone.
Yeah, on the phone.
Yeah. When I got to high school, I was like, that's not a pound.
So let's talk about the range. So the range is all the possible what?
Y values.
Y values the function will take in its lifetime. So this function is going to go down forever, right? To take on every lower range value of -infinity. But is it going to go up forever?
No, it goes to 3.
Yeah, the highest it goes is 3, but does it actually touch 3?
No, it's like 2.999.
Exactly. So it's going to be from -infinity to 3, but we use a curved bracket. Very good. Another way you could also write this, because remember we learned about different formats of writing this yesterday, you could also just say x is less than 3. So those are the two ways of writing domain and range based on the different notations. Yes? Yes, you may. Alright, how's everyone feel about piecewise? Cool. You're doing really well with it, by the way, your class. Good job. So,
Tell the people on the computer they're doing good.
what people on the computer?
Aren't you filming?
Oh, it's just filming, but it's not like live. You
Yeah,
know?
but they're gonna watch it at one point. They'll be like, dang, it's so hard.
They heard me give you a compliment. Alright, so now we're going to look at this one, and we're going to determine if these statements are true or false. So looking at this, the graph is not a function. So if a graph is a function, it needs to pass the vertical line test. Do you see any situation on this graph that does not pass the vertical line test?
Yes. The closed circle is called the open circle and it has the same point on line.
Yes, but is an open circle meaning that you're occupying that space really?
No, so it passes.
It does pass. So the open circles don't count when you're doing the vertical line test. You only look at the solids or the lines. So does this pass the vertical line test?
Yes.
Yes, it does. It is a function. So this is false. This is still a function. So did everybody get that? I see some people on their phones, so we're trying to make sure you understand why this is still a function, right? So does everyone understand why this is still a function?
Yeah.
Okay, very important concept in this class. So, false. So yes, this is still a function. So it's not a continuous function, but it's still a function. Now we're going to move into range. So pretend these are going on forever, the parts that have the lines, okay? So range is all the possible y values this function takes, right? So this function is going to go up forever, but is it going to go down forever?
No.
No, there's no arrow going downward. So this function has a bound range on one end, so it's definitely not negative infinity to positive infinity. That's false.
Can we just write f?
Sure. So the next one is f of x is undefined at f of x equals 9. So what that just means is x equals 9. They want you to look at that point on the graph and determine if it is defined there. So at 9, is there either a closed circle or a line going through 9?
There's a closed circle.
Good. So that is false. It is defined there. X-intercept is at 2, 0. True or false?
True.
True. Y-intercept at -1?
Yeah.
That's also true, right? So this is a really typical question that I would give you like on a quiz. Like, because quizzes I'm not going to have you actually graph. So you're going to be like analyzing graphs, you know what I mean, when it comes up. So does anyone have any questions about A through E here? Okay. Are we good to move on then? Alright, so let's talk about a step function. A step function is a function, a piecewise function containing all constant pieces. Is also called the staircase function. So it's called the staircase function because it has the look of being like a staircase. It's always made up of constant pieces. What did we learn that a constant function looks like earlier?
It's the same.
Good, it's a horizontal line. So step functions are just horizontal lines, pieces of horizontal lines in most cases, okay? So let's go ahead and move on to the next slide. We're going to graph a step function. So the way that we graph a step function, all of these are constant functions, right? These are all pieces of constant functions, which means that they're all going to be straight lines. So it's going to just be a bunch of straight horizontal lines here on different spots. So think of these as your y values and this is your x. So for the first one, I know that my y coordinate is going to be 1 for every situation, and it's going to start at 0, 1. But is it going to be open or closed here?
Open.
Open. Good. What's a value less than 0? Good. So at -1, it's still going to be at 1. And at -2, it's still going to be at 1. So as you can see, it's going to be a straight line. And this is going into infinity because it's not bound. Okay, x is less than 0 is still open on one end of the spectrum. So the next one, right here, between 0 and 2. So at 0, it's at 2. At 1, because it's between 0 and 2, so 1 is between that, it's at 2. And then at 2, it's at 2, but what kind of circle is it? Open. Okay. Now next is going to be -1. So at -1, it's going to be starting at 3, and it's closed, and then it's going to go on forever in that direction, right?
Yeah.
Okay. All right, so how does everyone feel about this? Graphing a step function. You feel like you could do it?
Great, we'll give them a lunch.
No, we still have one more example left. Thank you very much. Okay, is everyone ready to do one more example? All right, so this is a word problem. So kind of a real life situation where this would apply. So it says write a step function for airport parking costs and then graph. So basically 6 hours or part thereof, that just means 6 hours or less really, you're going to pay $4. Each additional 4 hours or part of those 4 hours is going to be $2. And then if you reach the maximum rate of $10, you get 24 hours of parking, okay? So I want you to think of these right here, these portions as your domain, and I want you to think of the money portion as your range. So basically, let's set this up. So what's the cheapest you can possibly pay for parking in this garage? $4. It's $4 for $6 or less, right? So if you spend X is less than or equal to 6, you're going to spend $4. So this represents price, and this is time. So for each additional 4 hours of parking, you're going to pay $2. So what's the next step up from paying $4? $6, good. And how long can you park for $6?
6 hours?
So you pay $4 for 6 hours, and then you can park an additional 4 hours for $2 more.
Oh, okay.
So how long can you park for $6? 4 extra hours. 6 plus 4. 10. So for $6, you can park between 6 hours and 10 hours. Why wouldn't I include the 6 there? Why is the 6 not included?
Because you already paid for this.
Yeah, you would have paid for $4 for 6 hours. If you go 6 hours and 1 minute, you're going to pay into the next range, right? But you can go up to 10 hours and still only pay $6. Now from $6, if it's an additional $2 for 4 more hours, what if you have to park 4 more hours? How much are you going to pay? Each additional 4 hours, you're paying another $2. So if you go to 10 and that's not enough for you, you got to pay another $2, right?
Yeah.
So you're going to pay $8, and you can do that anywhere from 10 hours to what? 4 more hours, so 14. Okay. Now, lastly, the next step up would be $2 more. You can pay $10. But what do you notice happens when you pay $10?
Then you get the 24 hours.
You get the 24-hour pass, so you don't have to worry about paying another $2. Again, that's the maximum cost, right? So if you park anywhere from 14 to 24 hours, you're going to pay $10, and that's where it caps off. So does everybody understand that concept that I was talking about throughout the problem? Okay. So that's basically how parking works. That's actually pretty typical for parking. So 24 hours, your car is going to get towed out of there if you park more than that. Okay, you can't park more than 24 hours, so cap it off there. So let's go ahead and plot this. So for $4, you can park up to 6 hours. Now, at time 0, are you paying for parking at time 0? No, you have to park a little bit. So this is an open circle starting right here, and that goes all the way until you get to 6, right? That you pay $4. Now, at $6, you can park from 6 to 10 hours. But if you park exactly 6 hours, you're still paying $4, so that's not included, so it's an open circle. But if you park 6 hours and 1 minute, you're going to pay the higher price. So that goes all the way from 6 to 10. And then at $8, you can park from 10 to 14 hours, but if you're parking exactly 10, you're not going to pay $8. So from 10 to 14, you're going to pay $8. And then lastly, if you want to park more than 14 hours, you're going to pay $10. all the way up until you can park for 24 full hours at that point. You already paid for 24 hours. And then from there, you can't do anything else because your car is going to get towed out of the lot. So we cut it off there, okay? So let's talk about the domain and range of this. So the 24-hour domain is going to be based on time. What's the minimum amount of time that you can park in the parking garage? 0. But is 0 included? Are you going to pay for parking 0? No, so we use a curved bracket. But 24, you can park exactly 24 hours, so that is included. So does everybody understand why one end is curved and one end is square bracket? Now for range, we're talking about cost. What's the cheapest the parking's ever going to be? $4. And what's the most expensive you're ever going to pay for the parking here? $10. Does that make sense? Okay. Does anyone have any questions about this one in particular? Did you understand through the explanation? Okay, so before we end